Okay. So my project was something so similar to the to our second assignment. I was working on brain tumor segmentation. Um, Here are some like statistics, the motivation behind it. So worldwide, almost 300,000 people were diagnosed with a primary brain or spinal cord tumor last year. And then the brain and other nervous system cancer, it's the 10th leading cause of that for both men and women. And worldwide, an estimated of 250,000 people died from primary cancerous brain and CNS tumor last year, and the 5-year survival rate for people in the United States with that is almost 36%, and the 10-year survival rate is almost 31%. And then what that means is it tells you like what percent of people live at least 5 years after the tumor is found. So the 5-year and the 10-year survival rate means that. Um, there has been a lot of machine learning based image segmentations that has been used, and the reason behind it, because it's cheaper and it fastens the process, and also it reduces the intra and inter observer variations, and it minimizes human errors, and it helps with improved diagnosis, treatment planning, and the follow-ups when compared to like oncologists doing it, like segmenting the CT or MR images manually. Um, so to this end, I chose to work on the segmentation of gliomas in preoperative MRI scans. And the goal of this project is to produce the segmentation labels of the different subregions and achieve like scores as close as possible to the competition winning algorithm with a couple architectural changes. So the data set I've been using is the same as we used for the assignment two. They are preoperative multimodal MRI scans, and we have for the evaluation, I use like 3 subregions as we did in the second assignment. One is the whole tumor, the second one is the tumor core, and the third one is the enhancing tumor. So when we just look like at the data sets more in detail, we see that it has 4 channels. And for the label, we have 3 channels. The reason why is like the 4th channel is the background, and we can see the subregions. And the metrics that I'm using for this project is the dice score and the Hausdorff distance. The dice score basically tells us how good they overlap on each other, like in this image. And the Hausdorff distance, it's the longest distance you can be forced to travel by like for example, these points over here. So we're getting the longest distance from this image. And the winner of the Brett's 2018 challenge is the architecture called SegResNet. Um, and in this architecture, it's a semantic segmentation network for the sub-regions, and it's based on an encoder-decoder architecture like it is in UNet. And we can see that the input is a 4-channel 3D MRI crop, and it follows by 3 by 3 by 3 3D convolution with 32 filters. And the ones over here, the green blocks, they're the ResNet-like block in the group normalization. And the output is also it has 3 channels. So I first started with running this challenge winner architecture, and these are the results that I got, but it was running like so slow. So for me it took 29 hours for 300 epochs. I was using one GPU, and the loss function that they used is the dice loss, and the optimizer they were using is the atom optimizer, with a weight decay value of this. So I just kept everything the same to get this results as the baseline results, and adding my architectural change. Like the goal was to see how my architectural changes affect the baseline results. And these are some sample predictions of the baseline results. So I decided to apply two different architectural changes. One is the change of the learning rate scheduler. So rather than the cosine learning LR, which is the stochastic gradient descent with warm starts, but in Monai, I was using Monai framework. They this one doesn't have the restarts, but other than that it's the same as the stochastic gradient descent. So I changed it to cyclic learning rate. In cyclic learning rate, there are three different approaches. One is the triangular, the other one's the triangular two, and the last one is the exponential range. And the triangular just keep the learning rate between some two values, the maximum one and the base learning rate. In the triangular two, they just reduce it, and the exponential rate, they reduce it exponentially. Um, so I started with trying those three different cyclic learning rate schedulers, and I saw that they improved the results. But since I didn't run it for 300 epochs, I am not sure if it's gonna improve the end results, but I hope it will. So when comparing these three cyclic learning rates, I figured out that exponential range would be the best choice for my case, and because it helps with the model converge faster, and at the same time it improves the dice scores, especially for the small objects. So this was what I got from this experiment. And then my project is not done yet, and so the other thing I will be trying is the dice loss rather than the dice loss itself. And the reason why I chose this is because in NNUNet, they're using this loss function, so I thought it would improve the results. So conclusion, as I said, with cyclic learning rates, the model converges faster, and then the improvement for the smaller or the harder to detect objects is higher than the larger or the easier to detect objects. And between all three cyclic learning rates, the exponential range gave the best results. So and since it is changing the learning rate exponentially, I guess that's why it converges way faster than the others. And the future work that I'll be completing by the end of this month, or till the deadline, is adding the Hausdorff distance 95 scores as an addition to the dice scores, and then seeing the effect of dice CE loss rather than dice loss only. And I will also add the performances of the regular units with the baseline SegRes unit and the enhanced version that I'm working on. And that's all. Thank you.
Okay. Yeah. Thank you for the presentation. I think the problem is very clear, right? Everyone working on the second assignment knows this task. I think you did a good thing is you have established the baseline, right? Using these the weaning method, you are able to get the result. By the way, did you reproduce what they are reported, or did you observe any of the discrepancies between your reproduced result and their reported result?
I just like directly run their code. So like I reproduced it, but like I got the same results just because
Okay.
they also using the built-in library, the
Yeah.
data set. So nothing was like
Yeah.
different than
Okay.
that.
Okay. Yeah, that's good. Yeah, it's better. You run their code if you are able to reproduce the result, then which means maybe everything is correct, right? So then
Mhm.
you can using this as a strong baseline, and trying to do some modifications as you are trying to do here is using a different learning rate schedule, and also trying different loss functions here. So I think the cycle learning rate schedule is a commonly used technique. The reason it will help improve is that the cyclic scheduling, right? So you go up, increase the learning rate, then you reduce, right? The suddenly this kind of cycle of increasing and reduce is that when you if you just keep reducing the learning rate, sometime you may stuck in a not very good local minima, right? And because of the small learning rate, you are not able to jump out of that local minima. But if you somehow increase the learning rate, right? We talk about the gradient descent, right? If you increase the learning rate, there's a chance and then you can make a large leap, right, in the optimization direction. Then there's a chance you can jump out of that local minima, then starting to explore maybe a better local minima, right? Because we know the loss landscape, they exist many local minima, right? So the ideal situation is that we want to find the global minima, right? So by doing this kind of cyclic learning rate, it's kind of helpful, to jump some of the not so good local minima, then explore maybe a better choice. Okay,
Right,
so
right.
yeah, so I think it's good you compare some of the convergence, rate with the usual cosine annealing approach, and also one thing you notice is it will also improve the performance for some of the maybe difficult classes. So it would be good, you can also present some of the visual comparison in the final report, right? So
Yes.
instead of these quantitative result is good, right? Definitely will shows the
Mhm,
improvement, but to demonstrate the point, right?
mhm,
Where does this improvement come from? Maybe it's useful to show some visual comparison, right? So these
mhm.
maybe enhance those difficult classes or small regions, gets better segmentation boundaries. And the same thing, for the loss function, right? So you want to do some more analysis. How does this help for the segmentation result? So I think that's the some of the suggestions I have for you for the final report, and I hopefully you are able to finish trying these different loss functions. And another thing, um, maybe worth to try is use the weighted dice loss. I don't know if you guys noticed for this Brett's data set, class are unbalanced, right? Some of the classes has more training samples, right, in terms of total pixels. Some of the classes occupy less number of training pixels. So it will help be useful if you can using some weighted, dice loss. Basically, you can count the number of training samples and using the inverse, the weights will be determined by using the inverse ratio, right? If one class occupy a large ratio, then you can assign smaller weights during the dice loss accumulation. So that can help kind of suppress some of the contribution come from the majority of the class, and also help the presence of those minority or less present classes. Okay, so that's
Okay.
maybe another thing to note. Okay. Okay,
Yeah,
great. All right, thank you for the presentation. Then
thank
let's
you so
move on
much.
to the next one. Yeah, thank you. So I think Michael, you are the next one, right?
I think so. So
Yeah.
let me
Yeah.
get the presentation. Let's see here. Can you see this?
Yes.
Or okay. So let me just start the slideshow. Okay. All right. Hi, and you can see this. All right. You can see the full
Yeah.
screen.
Yeah, I
Okay.
can see. All right, thank
Okay.
you.
Hi, my name is Michael Fielder. This is my project presentation for CAP 5516. So just a quick overview of the problem that I base it on. It was one of the original project ideas. It is an extension of the paper, a data set and benchmark for malaria life cycle classification in thin blood smear images. This was a paper co-written by Professor Chen. And the main goal of this paper is to detect infected malaria cells in an image containing multiple red blood cells. And the problem that we face is that it might take an expert 10 to 15 minutes per not cell, but per image to analyze all of the cells and attempt to find a malaria infected cell. So the idea is to create a model that can analyze one of these images and find all of the cells that are infected. And so the paper not only provides a model, but also a baseline model for detecting and classifying the parasites, but also a data set that was manipulated from microscope images to be more readable. So that's just a basic overview of the paper, the original paper. And then so my original problem statement is to experiment to see if the model can run on a microcontroller that can detect malaria. So originally the model runs on this phone app. And so the idea is that you can put the images into this phone app and then it can analyze, count the cells, and attempt to find ones that are infected with malaria. But my intention is to run it on a microcontroller, which is smaller, cheaper, and more energy efficient, and can hopefully run offline so that it doesn't rely on the need for a phone to analyze the images. And specifically, I'll be focusing on the binary classification task of detecting whether or not a cell is healthy, because there are multiple different types or stages of malaria infected cells. So my goal is to just detect if it has malaria and not the specific cell type. And so the baselines of the model is that it achieves an average accuracy of 95.36 in the paper and an F1 score of 89.91%. So this is only for the binary classification task and not for the individual types of malaria. For that, the accuracy drops into the 70s because of the fact that it is a more difficult task. And the reason that I make it a binary classification task is because, again, it's easier to handle on a microcontroller. And so this is just an overview of the architecture provided in the paper. So initially it uses a water shedding algorithm to individually segment each of the red blood cells. And then these individual red blood cells are passed into a binary classification network and then into a multi-class classification network. And then it tries to guess the individual classes, but I will just be focusing on this portion of the architecture. And in the paper, they use a ResNet 50 architecture to achieve this binary classification task. So the original data set is images like this, where it's the entire image of multiple red blood cells. And so what I did is that I created a new data set of just the individual cells that are segmented. So the idea is that this microcontroller should be able to handle a cell passed into it, and then it will be able to tell you if that cell is normal or infected. And so this is just an example of just one image that is deconstructed, and all now they'll be RGB images, but this is just to highlight the imbalanced data set present. So for just one of these images, it has only 2 infected cells and many non-infected cells. And so this becomes a problem because you have a lot less examples of infected cells in the data set. So, and that's the most important part of the data set, is trying to find out which ones are infected. So that becomes a problem, and especially for handling it on a device with such little memory. And so, yeah, that's how I edited the data set to be used on the microcontroller. And so the next thing is to look at the hardware details. So the specific piece of hardware I'm using for this assignment is the Arduino Nano 33BLE, which has become the de facto standard for handling tiny ML applications. So currently a lot of the examples and the recommended hardware in a lot of textbooks for this kind of edge computing is this specific one. And one thing to note is the limited amount of flash memory available, only 1 megabyte. So you have to load this entire model onto, only 1 megabyte of storage. So that becomes quite a problem to handle. And another thing to mention is that it has Bluetooth to send information, and also that it can take, you can send information through a Type B micro USB input on the front, which can be connected to the computer. And so just a little overview of the model details. So specifically, I'll be using a MobileNet architecture, which has become the preferred model to use for mobile applications. And so I came up with this one because this one in particular, because the hosted models on their website that have converted the models into TF Lite, which is used to load models onto edge computing systems, the model size is only half a megabyte, so it should be able to fit on to the model once it's been quantized. And so one thing to note too is that the accuracies are obviously lower, but hopefully, because I simplified the problem, the accuracy should be a little bit better. And so the general outline is to train the model regularly in TensorFlow, then convert the model into a TF Lite model, which is significantly lower in size, and then you can further quantize that model to reduce the size. And so the completed work so far is that I have obtained the necessary hardware to run the project. I have reformatted and successfully loaded the data set. So everything's pretty much ready to be trained. I'm probably going to start training this weekend, and then hopefully have a model that is fully trained and then can be converted and then loaded onto the Arduino Nano, which involves loading it onto their specific IDE in the form of a byte array, and then that's loaded onto the Arduino, and then you can pass it images and hopefully have it read and assess the images. And so, yes, I've also loaded the mobile. I've looked into how to load the model and prepare it for training, so everything is working in that regard. And so what needs to be done is to train the model, convert it into a TF Lite model, and then load the model's the byte array architecture that's generated from TF Lite into the Arduino, and then test the model on images directly on the microcontroller. And so that is hopefully the end goal, and hopefully it can receive accuracies closer to the baseline. And so that's my presentation. So.
Okay, all right, thank you, Michael. Yeah, I think yeah, the research problem is very interesting. Yeah, so you did. By the way, can you still show the slide?
Sorry. Oh, sorry.
Yeah.
Let me see.
Yeah, so I think yeah, these kind of tiny ML is quite, I think it is a very hot topic because, a lot of applications is very resource limited, right? Especially, for some of the medical domains, we cannot afford like a high end, like GPU workstation or servers because of the scales. So yeah, it also has a lot of practical value, right? If you are able to have this kind of very cheap, cost-effective microcontroller, is able to accomplish the job, right, at a very high accuracy, then I think that's very practical.
Yeah.
So for, I guess, have you working with these microcontroller before? You know how to, load the data.
Yeah. There's a lot of resources
Yeah.
related to
Okay.
There's actually a whole book
Okay.
related to TinyML, and it has examples of how to load models
Okay.
on specifically. So you essentially just convert it, and it gives you like a byte array.
Mhm.
So like specific hex values of what the architecture looks like after being quantized and minimized, and then you can upload that onto Arduino and send it straight to the architecture, or like whatever microcontroller you're using, and then from there
Okay.
it just becomes like loading the image. If I'll probably come up with some pitfalls, so we'll see. I'll try to do as much as I can,
Yeah.
because there's always problems that can
Yeah.
happen. So I guess it's a learning
Yeah.
opportunity.
Yeah, because you are also not just dealing with software, you are also implementing the hardware piece, right? So I was just concerned about if there's or you have a experience working on that, and so that may give you a lot of pitfalls, or maybe some other things you haven't
Yeah.
thought about before. Okay, but if you feel like there's a lot of resource and it's pretty much like a standardized, have like a specific pipeline you can follow, right?
Yeah.
Just having this module, then yeah, I think should be fine.
Yeah.
Another thing is when you have one specific challenge mentioned is the unbalanced data set, right?
Yeah.
So how are you going to address that problem? Because you have a lot of normal cells.
Yeah, because it's essentially a long-tailed distribution, but only with two classes, right? So I mean, the general idea of handling long-tailed data sets would be to like pre-train it, right, on something like ImageNet and do some kind of transfer learning. I don't know how beneficial that'll be in the case of this problem. I think most likely I'll just use some kind of what's the word, augmentations to the images to bolster the data set and to give more examples, because I think all it needs is probably just more examples of unhealthy cells, so that way it can just figure out, because all it needs to do is really figure out what the difference is between the two, and it doesn't need to specifically classify the specific kind of cell it is. So I think it should be able to achieve it. From your research, it seems like it's pretty like that part of it is pretty solved in terms of getting a relatively high accuracy. So
you can always since you are using existing architecture, MobileNet, right? So you can using the ImageNet pre-trained model and just fine tune on your data set. Yeah, but definitely try data augmentation. Those different augmentation technique pretty much built in, like in PyTorch, like core rotation, adding some color jittering, etc. So that will definitely increase the number of samples for those small training size classes. So in this way, see if you're able to, get some decent result. I don't think you will get like a very high accuracy by compare with like large models, because this is a MobileNet, right? So you will suffer for some of the performance degradation, but at least you want to get some reasonable performance. for both of the class, right? Because you have to think about it can be achieved overall can achieve very good accuracy, but it may just perform very well on the majority of the class, right? But doing terrible on the minority class, which is the infected cell, right? You can, maybe your data set has like 90% of normal cell, and your overall accuracy can be 90%, which is all correctly for the normal cell, but those 10% for the infected are all missing or misclassified.
Yeah, it's pretty much just like a tumor problem, the same exact thing where it's like you can get very high accuracies, but if you get low accuracies on, tumor, like brain segmentations with tumors in them, then what's the point of your architecture?
So
it's not doing
right. So when you tuning your model, you want to keep this in mind, right? So this model is able to do well on both of the class, right? So I think that's the important thing. Okay, so yeah, hopefully you can complete all these, and very interesting if you're able to deploy this model on this very cost-effective microcontroller.
It shouldn't be too difficult to train, so I'm gonna probably start training it this weekend. So it should be done by next week, and then I can focus on the hard part, which is probably going to be deploying it. So I'll do as much as I can with that. So
okay, all right, sounds great. Okay, all right, thank you. Then let's move on to the next presentation. Jacob, I believe.
Yep. Michael, could you stop sharing your screen?
Michael, can you stop sharing?
Yeah, sorry, I'm trying to get to it. Let's see here. Oh, geez. All right, sorry.
Okay.
All right. So I'm going to be going over trying to use optical character recognition to improve pill detection on the ePIL dataset. So this is one of the suggested projects from Dr. Chen. So the problem comes from trying to identify which pill we're dealing with So this is a common problem for doctors have to deal with lots of pills. It'd be nice to be able to speed up the process, and consumers, if something gets mixed up, it's better for them to have a way to tell what they're dealing with. Since there's an ever increasing number of pills, it'd be useful if we just had some computer technology to increase the speed at which we identify pills. So a little bit about the data set. There's 4,000, 5,000-ish reference images. So these reference images are pictures of the front and back of pills under extremely controlled conditions with controlled lighting and a clean backplate. Meanwhile, they have consumer images of some of the pill types. And these consumer images have a lot different settings, as in like brightnesses, it might be at different angles, could be blurry. And this is meant to test how robust your model is. So for each reference image, there's usually there's always a front and back of the image. So this would be your reference image or images, and it would come with a pill ID that you're trying to identify. And meanwhile, the consumer image might come with various backgrounds and some extra shadows that make it a little bit more difficult. This is one of the easier images to deal with. So the main challenge with this data set is that the reference images, we only have one image of each pill. So it's a one-shot task. So, and there are around 5,000 different pill types. So it makes it a very difficult task. So one way to deal with the limited amount of reference data is through augmentations. So we can apply augmentations to simulate what consumer images might be like. So obviously we can apply rotations. These are going to be a bit exaggerated. Some blurring to simulate cameras being blurry, and also some color jitter. So you make brightness difference, saturation, adjust the hue, and you can replicate a lot more of the consumer images you might see. So this deals a little bit with the limited data we have. The authors of this data set also propose some methods, some metric learnings. So they use softmax and cosine softmax loss, but they also use some triplet loss and contrastive loss. So they're trying to force their model to express their encoded. So whenever the models they're designing, such as ResNet, encode the data, they want the encoding to be meaningful. So these two are forcing the encoding to be meaningful, while these two enforce higher accuracy. So overall, their loss function for what they're trying to train looks like this, where they just put different weights onto each term. They did an ablation study on this where they just tried different weights and outlined it. Later on, I have not done it yet. I would like to implement this into my project. As for now, I'm working on the optical character recognition. So I'm trying to add additional features to the models themselves. So for example, if we have a reference image, we can perform character recognition and get some strings back. So this optical character recognition is just done with an off-the-shelf OCR model from EasyOCR, just an OpenCV. So you can get a string, and what I'm doing is using a one-hot encoded vector to identify basically whatever code matches with the one we detect, we turn it on, and we can pass this as an additional feature to our model. Sometimes, however, because this data isn't necessarily pre-labeled, we might not get our perfect match. So here you can see an image that'd be difficult for OCR to detect. This is supposed to be PA46, but we say we got PA48. I also have a none feature vector that I've added for whenever it doesn't match anything. This could also just be removed and just have all zeros. And essentially what would happen then is we're just looking at the ResNet model. We just wouldn't look at any kind of optical character recognition. So a basic overview, I'm just taking a backbone. I'm using different backbones such as ResNet and DenseNet. Right now I only have ResNet going. Then we perform optical character recognition. We get the combination of features, and we put that through a fully connected layer to get our predictions. As of the results I have right now, I've run on a small model, ResNet 34, using optical character recognition. I've got a mean average precision of 60, which is slightly better than just using the baseline ResNet 34. So plain classification just being, they just put the front and back images through ResNet and saw how accurate it performed. The multi-head metric learning, however, is performing much better, obviously much better at 95 than my current method. So obviously implementing the different metrics into my work would greatly improve it. But for the moment, I have a little bit of improvement over the baseline models. So for future works, obviously implementing the metric learning, that will help the encoding vectors. The OCR technique, because I'm using an off-the-shelf model, sometimes we're getting incorrect detections for the characters, which means my current method would just completely ignore that data. So we don't gain anything useful out of it. One method Dr. Chen recommended was using edge detection method. So we have an RGB channel, but we could also have an edge detection channel. So at the very least, if we aren't able to detect all the characters accurately, we would still have some information to go off that would improve the model. Currently, I'm using a small model, ResNet 34. That was just simply due to time. Increasing that to ResNet 152, I'm sure would have improved results. The authors have different metrics that I haven't yet implemented. that I would like to compare against. And that is it for my presentation.
Okay, all right, thank you, Jacob. Yeah, I think your approach is interesting by using the OCR as additional feature. Even though I think the metric learning approach, is better, but your method can be like a plug and play, right? So their metric learning, whatever the metric they are using, you can use as well, right? But you have extra component that as the OCR provide extra information to help improve the performance. But I think my question here is, why do you think about OCR in the first place, right? Why do you have this kind of, what motivates you or inspire you using the OCR? And yeah, maybe we start here. Like, which caused you to, think about using OCR to do this kind of task, and you think it may help?
Yeah, I mean, I guess based on the models the authors proposed, they're basically using ResNet and their metric learning. But like as a human, if you're going to look at one of these pills, like the first thing you're going to look at is like the characters that are detected. So if you had an OCR that was able to immediately extract those numbers and immediately connect it to a reference image, it would just save it seems like it would save a lot of time. You might get better results because basically none of what the authors do interact with the numbers directly. Not to say the ResNet models aren't able to learn some of the letters themselves.
Yeah. So here I want to understand. So here on the right, you have 4,902 pill types.
Yes.
So, and types means they have like a different ID, right? So on the left, you have like NDC, those number. If there's so I think not fully understand is that here type means in terms of shape, color, or there's more complicated, like a pill can have the same shape, color, but if there's a different numbers on it, then be considered like different types.
So they're just referring there's each type would be like a different we're trying to predict the original type, so they all, let's see. So like if it's a different shape, it's going to be a different pill type. They're all going to have separate IDs. So like the ID is what we're trying to predict. So if there's any kind of like variation about the shape, you're going to get a different ID.
Yeah, okay.
So we're trying to take these consumer images and identify like the original pill type it came from.
Yeah.
So these are like 5,000 different classes essentially that we're trying to predict on.
So that means the numbers like on those pills has a specific meaning that ties to or connect to the pill type, right? So here, the example you show here, right, 93, that's the front. Maybe the back is 4180. So it does has those exact information connect to the pill ID, right? 00937180.
Yeah. So yeah, each of the pill number, there might be like overlapping. So different pill types might have the same numbers, but they're going to have different shapes. So you can't completely rely on the character recognition, but it's a useful feature to have.
Yeah. Okay. Yeah. So I think that's the motivation, right? You wanna in your report, right? Why do you think about using the OCR in the first place to help? So you can just give this kind of example, right? So these are the characters on the pill, and it's present information related to the pill type, right? So then if we are able to extract this kind of information, then basically you are able to predict or maybe even directly output what type that is, right? Although like you said, right, there may be the same numbers, but different shapes. They consider two different types, but for some of the types maybe only have one shape. Then if you are able to recognize that number, then you basically have the label for that pill, right? So I think that will be a very good intuition, right? Why do you want to using the OCR, have this kind of idea to help improve the pill type recognition in the first place? Okay, so that's the motivation. Then when you do the method, can you go to that slide has the your network? Yes, this one. So the backbone means you take the image, right? You maybe using some of the off-the-shelf CNN like ResNet to extract some features.
Yeah.
And here OCR, so I guess you will convert whatever the recognized numbers into strings into like one hot encoding, right? You have like maybe 10 or maybe more types, then you just convert that into this kind of one hot encoding as the feature.
Yeah, that's exactly what's happening.
Okay. So how do you determine like the total? So what is the string or what the one hot encoding look like? How many you have?
So
Is this
like
like
since the original data set isn't like, it's not labeled or anything, and I can't label 5,000 of them,
Yeah.
I ran OCR essentially through it a few times for each image, and took the labels that came up. So like, say we ran this one like 5 times and 894 showed up each time, then I add it to
Mhm.
like the feature vector. And then if I come across 894 in practice, you essentially mark that one as what you found.
Yeah. Okay.
And then because these dimensions might be different, I'm trying to concatenate the this feature vector onto the backbones export. So there is like a fully connected layer just to reshape it a little bit
Okay.
to make sure that I can actually combine them.
Okay. I see. Yeah. Okay. Yeah, I think it does improve, right? So from your preliminary result does have like 2% of improvement. Maybe you can maybe further refine it, like how you represent the features from the OCR, right? Doing some, word embedding something, right? Like from the NLP, right? Do some word embedding. Maybe that will further improve. And yeah, if you have time, you can also try like, so I think my suggestion when I read your milestone report is, generate an edge map, right? Using a very simple edge detector, right? Generate an edge map. Then you can consider like the false channel, right? Original RGB, then consider the false channel, then, feed that into the network, maybe in those edge information, which may contain some of the character, right? The numbers that may also useful. Okay.
Yeah, when you suggested that, I thought it made a lot more sense than kind of this
Yeah.
approach, because this is very noisy. Like if this one letter of this gets detected off, basically we gain no information because it's not matching with anything here. But with edge detection, if a little bit's off, you still have the rest of the digits to take some information from.
Okay. All right. So there's one question from Joe. Why did you choose the FC layer versus as input to the backbone? Joe, can you maybe rephrase your question if you don't mind?
Yeah. I was just wondering if you bring up the architecture, why you chose they're going into the fully connected layer together, right?
Yeah.
Yeah. I was just wondering why you only use like maybe one fully connected layer to model that interaction, or I'm just wondering what your approach was.
Yeah, essentially my thought process was like, this is an encoded vector of like the input. So it's been encoded for the backbone. Like we're not taking the backbone's like predictions on which pill type it is. We stop early whenever it's like encoded. So we concatenate the two encodings and we can pass it through a fully connected layer. And the output of this is just gonna be like a dimension of 5,000 by 1, where it's like the probability of each class happening.
Okay. Yeah, I was just wondering because it seems like you could like kind of model using those those FC layers, like the interaction between maybe how accurate the OCR is versus the like ResNet prediction. So that's kind of
So
interesting.
like,
Yeah.
you're saying like some kind of like just predict off the OCR straight to predictions and see how that does as part of like a loss function, or?
I think you have it there. I'm just wondering if maybe more layers would help, like understand how much to rely on the OCR.
Okay, yeah.
Because of that, I don't know how accurate that model is versus the ResNet model, which will actually, you know, has a lot of parameters to learn like how to model it. So it's just kind of interesting, but I do kind of like your approach.
Yeah. I guess one of the problems with the OCR model is it is like off the shelf. So it's not really trained for this in particular, just because I don't have like the letters for each of these. So it's using some like pre-trained weights.
Mhm.
So there's only so much I can rely on, like the OCR.
Yeah, that's kind of what I was thinking. It's like you're kind of ensembling these two methods, and you want to learn how much to weight the prediction from that OCR model. So it's just interesting.
Yeah, another way you can think about is OCR, right? So there's a lot of deep learning based OCR methods. Take the image and output those, you know, characters, right? So in the middle, you know, some of the OCR, they're using CN or whatever architecture, right? So you basically maybe look into some of the deep learning based, just take the pre-trained model and apply that on your data, input data, then get the features, right? Not just the output OCR, right? So here you output those characters, then you manually convert into like one hot encoding, right? So here I was saying don't output using the output characters, but take the intermediate feature, maybe the last layers or column features before they output like OC characters, and take that feature and concatenate with the lower backbone, right? So in the red one, then the features will be focused on the characters, right? Because you know you can think about the next step for the OCR stream is going to be output those characters, right? Those information, the feature will contain information focused on those regions, right? But for the second one, the backbone maybe contain like a holistic feature, you know, the entire image. So in a way, you can say the OCR stream like has some attention, right? You focus on those character regions. And so that's another, you know, approach you can try. Okay.
Yeah. So essentially just like two feature extractors
Yeah.
being merged. Okay.
Yeah. So yeah, the upper one is like OCR pre-trained, right? Just maybe focus on characters. But the second one can be any, you know, image pre-trained, like ImageNet, ResNet, ResNet pre-trained on ImageNet. Okay, so those are something you can try.
Yeah.
Okay. Yeah, Zach has one suggestion about OCR. Zach, you wanna?
So it was actually the thing that you suggested about
Okay.
using a machine learning model and just using the output features
Yeah.
as opposed to trying to make
Yeah.
a one hot vector.
Yeah.
Yeah,
Yeah.
that makes a lot of sense. Yeah.
Yeah. Okay. Yeah. Very good. Okay. All right. So I think we have to move on. But thanks a lot for you guys. Those very good questions and discussions.
Yeah,
So
thanks guys for your suggestion.
yeah. All right. Tao, if you're ready, please go ahead.
Okay. Okay. Hi everyone. So my project is about a dynamic network for efficient 3D medical image segmentation. So we know that the 3D medical images are composed of multiple slices, and there are basically two kinds of methods to deal with these 3D medical images. So one is like the using the 2D networks, such as the 2D UNet. So these works, they process the input slice by slice and then segment each slice independently. And another kind of method is using the 3D networks to process a volume of multiple slices together, so they can leverage the connection between each slices. So the problem that both the 2D networks, the 2D methods and the 3D methods, they need a lot of computations to process the 3D medical images because it has hundreds of slices in each image. So my project is trying to use the dynamic inference method to improve the model efficiency for the medical image segmentation. So we see that like here showing the figure, both the 2D networks and the 3D networks, they process the every slice equally. That is, they are using the same model and also same number of computations to process each slices. But in 3D medical images, we know that the slices, the properties are very different across different slices. And showing the figure, like the first one, we see that there are multiple types of tumors in the slices, and also they are in very irregular shape. So those slices are like very hard slices to segment it precisely. So we may need a stronger and a larger model to deal with those hard slices. And for these slices in the middle, they may only contain like one type of simple tumor or low tumors. So these slices are very easy to segment, and we can just use a small model to process those slices. And for the last one, they may contain nothing. So basically they are just background. And for those slices, we can just skip them to save the computation. So basically we are trying to to process the hard slices using a large model and the easy slices using a small model. And those background, we can just skip them. And in this way, we could potentially achieve a better accuracy efficiency trade-offs compared to using a single model to process all the slices. So the method is, so this is the method overview, and it basically has two components. One is the DCE network and another one is the model bank. So the DCE network is to decide which models in the model bank we want to use for a given input slice. So the framework is that for given a input slice, we feed it to the DCE network. And the DCE network is simply more formulated as the classification problem. So basically it takes the input and make a prediction, like which class is the input. So for the 0, we just corresponds it to the skip, and 1 we just corresponds it to the model 1, and n to model n. And after we select the model, we just use the selected model to segment the input slice. And then in this way, we can achieve a dynamic inference based on the input. Then that's the training for the homework for the framework. So there are basically 2 steps to train the whole framework. The first step is to train the model bank. So the model bank is basically just a group of different segmentation models. So basically we can train them independently following like the standard training schedules. But here to save the training time, I'm training them jointly. That is, I just like ensemble their loss and take the average loss and the final training loss. So basically, as the equation shows, the dice loss J is the training loss of the model J, and the final training loss is just the average of all the training loss. So that is the first step to train the models in the model bank. And in the second step, we are going to train the DCE network. So as I mentioned, so I am formulating the DCE problem as a classification problem. So so the first thing is to generate the classification labels for the DCE network. So to generate the training labels, I just use the model banks in the first stage, and I just feed the training the input slices in the training set to all the models in the first stage, and then for each slice I can get the dice score and the corresponding computational cost for each slice, and then we can use this to generate the labels. So the intuition is that basically for a given slice we wanna choose the model that has a high dice score, that is the S here, and we say no computational cost, that is the F here. So basically we want the ground truth to be the model has a high dice score but no computational cost. So we can basically follow this equation to determine the labels for each slice. And here the PF is the number of pixels of the foreground objects. So if it is a pure background, that is the number of foreground pixels is 0, then we just assign to be 0, that is a skip operation. So after we get the classification label, then we can just train the DCE network as a simple classification problem, just using the standard cross entropy loss. Here I'm using the weighted cross entropy loss. I put more weights on the models and lower weights on the skip operations. So in this way, I put more weights on the segmentation model so it can achieve a better performance. Okay, then that's the experiments. So for the experiments, I'm using the brain tumor segmentation 2019 challenges. So it has 335 cases for training and 125 cases for validation. And it has 4 classes, and I'm pre-processing those into 3 classes, just as we did in the homework. So for the evaluation metric, for the segmentation accuracy, I'm using the dice score and the Hordorf distance metric. And for the computational cost, I'm using the FLOPS. So those are the standard metrics to evaluate the accuracy and the computational cost. For the implementation details, so I first jointly train the models in the model bank for 400 epochs, and then I use those models to label the input for training the DCE networks, and the DCE network is trained for just 50 epochs. And for the models in the model bank, I use 4 models, so two 2D unit of different network weights and 2D trans BTS of different depths. So the trans BTS is just a transformer segmentation method. And for the DCE network, I'm using a small version of the ShuffleNet. So then this DCE network, the computation cost is much smaller compared to those segmentation networks. This is the results on the brain tumor segmentation dataset. We can see compared to previous method, the dynamic network, in terms of performance, it's not like always the best, but it's still comparable with most of those previous methods. And in terms of the computational cost, we can see it is much lower than all the previous methods. It's basically about 10 times reduction in the number of FLOPS. And this is a visual comparison of the dynamic network and previous method. So we can see like the dynamic network achieves like in this area, it has fewer like misclassifications in the pixels, and also it has better segmentation results in those details compared to the previous method. And this is an emulation study about the method. So basically, because I have 4 different models in the model bank, so I just like train them following the standard way and to show what's their performance and what's their computational cost. And as we can see here, the smallest one, the first model, it has the lowest performance, but also the lowest computational cost. And for the largest model, the fourth model, it has the highest performance, but also has the highest computational cost. And for the dynamic network, it basically takes the advantages of both the large model, the good performance in the large model, and the low computational cost in the small model. So we can see the performance is basically comparable with the largest model in the model bank, but the computational cost is also comparable to the smallest model in the model bank. So this shows that the decision network, it can intelligently assign the input to the appropriate models in the model bank and achieve a better accuracy efficiency trade-off than just using a single model to process all the input. So there are still a lot of work to do in the future. First is that I may need to do more evaluations on other data sets. And then I may need to do more emulation studies, like to show, for example, the effect of different decision networks and also the different choice of the models in the model bank. And also there are some other further improvements that I'm thinking about to improve the current method. So one is that currently I'm formulating the decision process and the classification problem, because that's simple. We can also try to formulate this as a reinforcement learning problem, and that may make more sense in terms of the decision problem, but that would be more complicated. But potentially it could achieve better performance compared to just this formulated as a simple classification problem. And also for the model bank, currently I'm using different multiple individual models, and they are going to consume more memory cost compared to one single model. So one strategy to deal with this is that we can train a super model. That is, one model can run at different network weights or different network depths. Then we only need to keep one model instead of multiple individual models. And also in terms of the dynamic inference, we can also, so currently I'm doing the dynamic inference in terms of the model size, but we can also try the dynamic inference in terms of the input resolution. So basically we can assign, we can use a higher resolution for those complicated cases and the lower resolution for those easy cases. And we can also even combine both the dynamic input resolution and the dynamic model size together. So those are just some future directions that we can further improve the method. So in concluding, the dynamic network learns to intelligently assign different computations to different input based on their difficulties. And it shows that it could achieve better accuracy efficiency trade-offs compared to using just one single model. Yeah, that's all for my presentation.
Okay, all right, great. Thank you, Tao. I think this problem is very interesting. The motivation is clear, right? So based on the observation of those MRI or CT volumes, right? Each of the different slices, they contain different content, right? So that's why, we don't have to apply the same network, right? Let's say you have a very heavy, 3D or maybe 2D ResNet 100, right? It's not necessary to apply the same network for each of the slices, right? Especially for some of the slices only contain like a background. Then a simple measure based on the pixel intensity, you can easily determine, okay, I'm going to directly output all 0 for these entire slides because there's no foreground. And for some of the easy slices, then a small network maybe already suffice to make a very good prediction. You don't need a large network to get a very accurate segmentation because there's just 1 or maybe 2 very simple tumor type, and the tumor region is very small. Okay, so I think, yeah, this is interesting idea, and I'm glad that you are able to make it work and demonstrate it does able to improve the efficiency, right, as compared to some of the large network, but also is able to maintain very good accuracy because, in your model bank, you do have very high accurate, high precision network, right? Those 3D trans-BTS, the 2D trans-BTS large model is able, those high capacity model is able to help you to, segment those difficult cases. Yeah, and in the end, I think 2 future directions are definitely very useful, which is kind of like a limitation of your current method, right? The memory cost, because you have the model bank, right? Right now you only have 4, right? What if I want to maybe have a more flexible trade-off? I need to or deploy 10 models, right? Then you have to think about, for each of the device, I have to preload 10 models, then select, switch between them. So it will be good to have a single model that you can adapt, maybe adjust the model width, right? That to achieve this kind of computation cost, trade-off. And yeah, the decision network right now is kind of very simple, right? Treat it as a cost-efficient task. Maybe RL will have a better, effect to make a more accurate decision, right? What kind of network you want to use. Okay. Yeah, but I think overall this is interesting, and yeah, I think this is good. Okay, so is there any questions? Okay, great. So I think this is a very good start for the project presentation. So I think you guys are making very good progress. The presentation is very clear. So I think we can, for the next presentations, the student can follow this class as an example. Okay. But for the next lectures, we have 5 presenters, so we only each one will get to like 15 minutes. So let's when you prepare the presentation, you don't have to prepare so many slices, but you do have to make your problem statement, method, and the progress very clear. So keep the presentation under like 8 minutes. So I will love to have like at least 5 to 7 minutes to give you feedback or ask you questions to help you improve. Okay, so just keep in mind, keep your presentation under 8 minutes starting from the next lecture. For today's, we only have 4, so we have more time to help you to present some of the details. Okay. All right. Thank you, everyone. We're gonna stop here, and I'll talk to you next week. Okay, everyone, have a nice weekend. Bye.